So instead of answering questions like we did last week, where we were talking about is the population mean greater than 200, or is the mean scoop size larger than 108 grams or whatever, those sorts of hypotheses. Now we're going to have hypotheses that are talking about two different populations and comparing them to each other. So it could be, is there a difference in the average scores between men and women taking this test? Or it could be, do people shopping in person tend to spend more than people shopping online at our online store? It could be, does this new ice cream store have larger scoops than the old ice cream store? And so the idea here is that we're going to have samples from both groups, and we're going to compare the means of those samples. And of course, anytime we take two samples, we're probably going to find different sample means. But the question is going to be, is that difference large enough that it's convincing us of something, just like last time, right? So last time, remember when we had the hypothesis, the mean is larger than 108? 108.2 wasn't large enough to be convincing, but 115 was, and 110 was borderline or whatever, right? So we had to do the math on that one. So it's going to be the same idea. If we have two ice cream stores and we get a sample mean of 107.5 and another sample mean of 108.9, those are kind of close, but they might be far enough to be convincing. We're going to have to do some math and figure out if they're far enough apart that we're really convinced. But before we get into the math, we have to talk about how there's actually two different structures for setting up tests between these two populations like that. So the two structures we want are called independent samples and paired samples. So with paired samples, each person or object in the first sample has a direct link with exactly one person or object in the second sample. And often that link is that it's the same person or the same object being tested a second time under different conditions. Right, so if I want to know, does this blood pressure medication actually reduce blood pressure? What I might do is I might test a person's blood pressure and then give them the medicine, and then test that same person later after the medicine has taken effect and see if their blood pressure went down like it was supposed to. If I did that for a bunch of people, that would be paired samples, because then what I would have is my non-treatment group, my control group, would be everybody in the study before they took the medicine. And then my treatment group would be that same group of people after they took the medicine, after they had the treatment. And because it's the same people, that's paired samples. And we're going to talk about some of the pros and cons of paired samples, because the other way to do this with independent samples would be just to have totally different groups, right? We could have one group who took the medicine and one group who didn't take the medicine. And they're just totally different sets of people, and we can measure their blood pressures. So, I have some examples. I have some examples coming up. And we're going to do some examples, make sure we can identify what type of test these things are. And there might be a couple of tricks in here. We're going to try to identify what types of tests we're talking about with each of these examples, and then we're going to talk about the pros and cons, why we would use one over the other. So the first example is you perform a blind taste test between two potential recipes for a new product. You gather 50 people and have them rate each of the two recipes on a scale out of 10. You want to know if there's a significant difference in the mean rating of the two recipes. So just think for a few seconds, and try to figure out what type of test this is. Okay, so because all 50 people are rating each of the two recipes, this is going to be a paired test. Because if Bob rates recipe A 7, and then Bob rates recipe B a 5, right? We can link those two data points. We can pair them, right? What is Bob's rating for recipe A versus Bob's rating for recipe B? Right, that's the pairing. And so we can do that for every person in the sample, all 50 people. All right, in this example, you know from past research that when you ask people how much they'd be willing to pay for your product, the population mean is very close to $25 with a population standard deviation of 450. You're planning on adding a new feature, so you gather 50 participants in a survey and ask them how much they would be willing to pay for the product with the new feature. You want to know if the mean valuation of your product's value is significantly higher given this new feature than it is without the new feature. So this one is our first trick. This is not paired and it's not independent samples. This is a one sample test. This is what we did last week. We're only doing one sample here. We're asking them one question. How much would you pay for the product with the new feature? We're not asking the people how much they pay for the product with the old feature because we already have past research that tells us that number is $25. So what we're doing now is we're taking one sample, asking them one question, and we're comparing their answers to a fixed value, $25, which comes from our previous research. All right, if we wanted this to be paired samples, we would have to ask the same people to rate the products with and without the new feature. If we were doing independent samples, we'd have to get two different groups of people. One group to rate the products with the new feature and another group to rate the products without the new feature and compare those samples. In this case, we're doing neither of those things, right? We're just getting one group to rate the products with the new feature and we're comparing their ratings to the established value, $25 that we already had from prior research. So this is a one sample test like we did last week. And so sometimes when we're comparing two groups, this is the way we do it, right? We might already have lots of good research on one of the groups. It may be the case that we just don't even need to sample that group if we have a sufficient level of confidence that we know what's going on with that group already, right? We have another group which we haven't researched as much. We want to compare them. Well, we can just do one sample. We can just sample the new group. All right, the third example here. You want to know whether a particular injection has an effect on blood pressure. You gather 100 study participants and you divide them into two groups of 50. You inject one group with the drug and the other group with saline, right? That's just a placebo, I think, like we talked about way back at the beginning of the course. So that's called blinding, right? Each group won't know whether they're the control group or whether they're the treatment group. And you don't tell the participants which group they're in. And then 5 minutes after the injection, you measure the blood pressures and compare the results from the two groups. Right, so this is pretty clearly independent samples, right? It's two totally separate groups. Right, for paired samples, it would have to be the same group twice. Right, there's no pairing between these groups. We can see what was Bob's blood pressure and what was Allison's blood pressure, but you know, there's no pairing between them. All right, another example here. You order 30 kilograms of product. It comes from 1 or 2 packaging centers. Shipments coming from city A are always exactly 30 kilograms. But you've noticed that shipments from city B are frequently a bit over or under 30 kilograms. You look at records of your last 35 shipments from city B to figure out if the average is significantly different from 30. Oh, sorry, I see some messages in the chat here. Okay, good answer. Yes, so this one is one sample, right? Because we're only actually sampling from city B. We're not sampling from city A. Whatever city A is doing, their shipments always seem to come in at exactly 30 kilograms, so we don't need to sample from them. We already know what's happening with them, right? So it's a one sample test. All right, so you're studying a species of bird, and you know from past research that the population standard deviation for the weights of males is 5 grams, and the population standard deviation for the weights of females is 3.8 grams. You weigh 45 males and 39 females to test whether there's a significant difference in mean weight. So this one's independent, right? Because we have the males and we have the females. Those are the two groups. They're separate. There's no link between them, right? You can't say this one male is linked to this specific female in any particular way, right? And a real giveaway is the fact that the sample sizes are different, right? When we're doing pairing, each data point in the first group has to be paired with a single data point in the second group. So the two samples will always have the same sample size in paired samples. For independent samples, they could have the same sample size, but they don't have to, right? In the blood pressure example, they were both groups of 50, so they had the same sample size. But in this example, they're different sample sizes, right? There's 45 males and only 39 females. So whenever you see that two different sample sizes, you know that has to be independent, right? There's no way it could be paired. All right, just one or two more now. You want to know which of two online retailers has the lowest price. You randomly pick 250 products that are offered by both retailers, and you compare the prices on each website. You then compare the results to examine whether there's a significant difference in prices. So this one is paired. And the reason it's paired is because we've picked 250 products that are offered by both retailers, and we're comparing the prices on the two websites. So in other words, if we're looking at, say, toilet paper from a certain brand, right? That brand's toilet paper costs this much on website A, and that same brand of toilet paper costs a certain amount on website B. That's the pairing. We can look at the price of this product on each of those websites. So it's paired. If this was independent samples, then it wouldn't be the same products, right? We would get one randomly selected group of 250 products from website A and a different group of products from website B. The fact that it's the same products across both sites is what makes it paired. Okay, I think this is the last one. Is this the last one? Yeah, this is the last one. You're testing whether being within 1 kilometer of a subway station increases condo prices. You take a sample of 60 condos within 1 kilometer of a subway stop and another sample of 150 condos that are not within 1 kilometer of a subway stop, and we compare the results. So this one is independent. Again, the giveaway of you have two different sample sizes, right? With those two different sample sizes, it has to be independent. There's no other option. Okay, so those are all the examples. Since now we have an idea of which is which. The next slides are about the math. But before we get into the math, I just want to talk about the pros and cons, why we would do one over the other. So if we look back at the example of the products on the websites, this one is a really good way to understand why paired samples are good, right? Because literally we could be comparing apples to apples here, whereas with independent samples, we may be comparing apples to oranges, right? How much do apples cost on website A versus how much do oranges cost on website B, essentially, right? The fact that we're making sure we're comparing apples to apples, we're comparing literally the same products to each other, has some obvious benefits. That obviously seems better, right? And it is better because we're controlling for certain types of bad luck, right? If you have these two websites and you randomly set products from website A and then randomly set different products from website B, there's always a chance that the products from website B that you selected just happen to be some of the more expensive products there. And the products from website A happen to be some of the less expensive products there. So that's going to make it look like website A is more expensive than website B, even if overall that's not true, right? There could just be some sampling error just because of bad luck. But by picking the same products from both websites, you eliminate that kind of sampling error, right? You don't eliminate sampling error entirely because there's always the chance that some products are more expensive on website A and others are more expensive on website B, and you just happen to pick more of the ones that are more expensive on website B. But you eliminate a large chunk of potential sampling error by comparing apples to apples, right? And we can see this when we're dealing with people as well, right? If we're talking about blood pressure, when we're doing independent samples, if we happen to do group A and group B, and we're trying to test whether a drug works, a blood pressure drug works, but the people in group B just happen to have higher blood pressure anyway, then that could interfere with our test of whether the drug is effective. So having paired samples controls for this. We have less possibilities for sampling error. Mathematically, paired samples are stronger. If you do a paired sample test with 50 people, that's stronger than doing an independent sample test with two groups of 50. Right? So for the same sample size, you get much stronger results. Right? 50 people in a paired test is stronger than 100 people in an independent test. So there's a lot of advantages to paired samples tests, but they're not always possible, right? So if we look at this example, right, the male birds versus the female birds, right, it's not possible to vary the conditions here, right? We can measure the same person's blood pressure when they're on medication and when they're off medication. That's easy enough, right? But we can't measure a bird's weight when it's a male and then the same bird when it's a female. It doesn't work that way. Right? And then there's this one. We can't measure the price of a condo when it's close to a subway station and then the price of the same condo when it's not close to a subway station. It doesn't really work that way. If they build a subway station, that could be a nice experiment, right? What was its price before the subway station was built, and then what was its price after the subway station was built? But it takes a while to build a subway station. A lot of time passes in between, and prices in the market will be changing that entire time. So it would be difficult to control for all those price changes in the market. So doing a paired test here would be more difficult. What you might do is you might do what's called matching. So matching would be where you're not going to measure the same apartment or the same condo twice, but what you might do is you might try to find a condo that's very, very similar, right? You might say this condo is close to a subway station and it's a 2-bedroom condo with 1 bathroom and this square footage. And then we find another condo that's not close to a subway station, that's also 2 bedrooms, also 1 bathroom, has the same square footage. They're both on the 3rd floor, right? Find condos that match really closely, except for the one variable you're testing, right? And so with this matching, if you do that, then that can be like doing a paired samples test, and you can use the same sort of math as you would for a paired samples test. It can be a bit of work to do this matching, right? But sometimes you'll see that done. The other thing that can happen with hold on, but someone's not muted. Let me I can just mute people. Anyone else unmuted? Okay. Great. The other thing that you get with paired samples that can be an issue, if we go back to the first one, right? These potential recipes. You know that when you're trying something new, sometimes the first bite is different, right? Maybe better, maybe worse, but often the first bite is really important in a taste test. So if you're testing the same recipe, if you're testing two different recipes, which one gets tasted first could be really important. Right? So it might be that recipe A and recipe B are actually equally good, but participants are going to rate whichever one they taste first higher. That could be something that's happening, right? And so this is called an order effect, right? The order that you measure it makes a difference, right? And we can see this in a bunch of things, right? With the blood pressure, right? Some people are a little bit nervous around medical stuff, and maybe the first medical thing is the first measurement or whatever is just going to catch them when they're more nervous, and the second measurement is going to catch them later when they've maybe calmed down a little bit. Right, especially if they're like anticipating getting a needle coming up soon, right? Some people are going to have a response to that. Learning can cause order effects, right? If you're giving the same person the same test twice, you expect them to perform better the second time, just because they learned from doing it the first time, right? So there's all sorts of situations where the order matters. Now, sometimes you can try to control for that by randomizing things, right? You can, like with this taste test, you can get half of the people to try recipe A followed by B, and the other half try B followed by A, right? But sometimes that's not always possible, right? Sometimes, like if you're giving someone a drug, it's easy to test them before the drug and after the drug, but doing it the other way around is much harder because you have to wait for the drug to wear off, right? You'd have to give them the drug, test them, and then call them back on a separate day, maybe when the drug's worn off, to get the second test, right? So that might not be practical. So whether you're going to use independent samples or paired samples is going to depend on the practical realities of what sort of test you're doing. Mathematically, paired samples are better. They're just straight up better. But if you can't account for their downsides, if you can't stop there from being biases due to the order, then you're going to have to do independent samples. Right? It can be also harder. It could be harder to blind people if you're doing paired samples than when you're doing independent samples, right? If you're giving the same person an actual medication and a placebo, that could be easier for them to tell which one was which than if you just gave them one shot and didn't tell them if there was a placebo or a real thing, right? Just the experience of having both might let them actually, feel the difference. There's also room for clever experimental design, right? So if you're testing tires, you want to know which brand of tires will last longer under real world conditions. So you might think, okay, well, we're going to do independent samples. We're going to give group A tires from brand A, and we're going to give the second group tires from brand B. How could we pair this? Well, to pair it, we'd have to give the same people tires from brand A and then tires from brand B. And then we run into problems where the whole test takes twice as long. If we were going to do 6 months of driving on them, well, now we have to do 6 months here, followed by another 6 months. And so the whole project takes a year instead of taking 6 months. But also, now we have to worry about road conditions, right? If they were on tire A in the winter and tire B in the summer, that's not a fair test. So we have to wait longer. We have to wait until next year. It seems like there's a problem. But if you're clever, you might think, okay, well, what if we give each person 2 tires from brand A and 2 tires from brand B on the same car at the same time? So then we can tell that both tires have been driven under the exact same conditions, right? They've been driven on the same days, they've been driven the same distance, they've been driven at the same temperature by the same person, right? We're controlling for a lot of variables this way, right? So by mixing up the tires that way so that each person is driving on brand A and brand B at the same time, you can do a proper paired samples test. Okay, so that's all the sort of background stuff. So now what I want to do is I want to go through the actual math of how we do a paired samples test. So I'm going to show you a couple of slides, but then I think we're going to switch over to the whiteboard and just go through an example. It's easy to do it's easier to see what I'm doing with an example. Okay, so to do a paired samples test, we look at each individual in the two samples and you subtract the results. So with say the taste test example, you know that Bob rated this recipe A 7 and he rated recipe B a 5. So you can subtract those, right? 7 minus 5 is 2, right? So the difference in Bob's ratings was 2, right? And if you do that for everyone, now you have this new column of data, which is the differences. And what you're going to do then, mathematically, is you're going to do a one sample test like we did last week, just on those differences. Okay, so for paired samples, the math is actually the same math as for one samples. We just have to do some subtraction first. For independent samples, we're going to have some more complicated things, right? You'll see that. I think I'm going to save those for next week. Like I said, I'm going to do a shorter class today and then do the bigger class next time. Okay, so this slide talks about the differences and similarities between the one sample test from last week and the paired sample test from this week. So step one, remember, was writing hypotheses. This part is a bit different. We're gonna have to do some examples to show you what the different sorts of hypotheses look like. A common one would be, you're testing if group 1 has a higher mean than group 2, right? And you can see what the hypotheses here look like, right? If group 2 has a higher mean than group 1, right? Because mean 2 minus mean 1 is greater than 0. That says that group 2 has a higher mean than group 1, right? And then the null hypothesis is the opposite of that. And so we're often going to see zeros here. Like I said, we're going to do a bunch of practice with writing hypotheses, because this is sort of the biggest difference between this and last week. Because then when we get to step 2, finding the critical value in the rejection region, it's exactly the same. Step 2 does not change at all. Step 3 also basically doesn't change. We can write it differently. You can see that this test, it looks a little bit different. We have D bar instead of X bar, but it's actually really the same, right? D bar is just the sample mean difference, right? Just like we had the sample mean last time. One thing to note is that with these paired samples, we're always doing t-test. I've never seen a paired samples z-test. I don't think, it's hard to imagine a situation where you would know the population standard deviation of the differences between the two groups, but you wouldn't know the population standard deviation, so you wouldn't know the population mean difference. It's hard to imagine a situation where that would happen, right? So that I've never ever seen paired samples z-test. It's always t, right? There's nothing mathematically impossible about it. Mathematically, you could do a paired sample z-test. It's just that it's never actually done, right? We're always doing paired samples t-tests. And then step 4 is exactly the same in terms of how we carry that out, right? We have our rejection rule from step 2, and we have our test statistic from step 3, and we compare them. So like I said, the biggest difference is step one. So we're going to focus on step one for a little bit, and then we're going to do an example where we go through the full thing. Yeah, so we're going to switch over to the whiteboard here. Okay, so let's talk about some different claims. Group one has a larger mean than group two. So we might write this, mean one is larger than mean two. All right, this is when we might write this. And this is fine. We can absolutely write it this way. But sometimes we want to write it in a different way. So we could also write that as mean one minus mean two is greater than 0. All right, you can see that mathematically these are the same. You could also subtract it the other way around. Mean 2 minus mean 1 is less than 0. Again, this is mathematically the same thing. So we can write this claim in 3 different ways. Now, one nice thing about these ways is that the 0 becomes visible here, whereas the 0 is actually hidden for this one. And that 0 is something that we're going to be using when we do the math. When we do step 3, that 0 is going to show up. And if you don't have it, if you write it this first way, then it's easier to get confused on step 3, right? There's a spot where a number needs to go and you don't have that number up here, right? Because it's a 0 and it's just hidden, right? The 0 is hidden in this when we write it this way. Whereas if you write it the other 2 ways, the 0 is not hidden. You can also see that because we have 2 different options for how we subtract, we can do group 1 minus group 2, or we can do group 2 minus group 1, then that gives us the option of doing a right-tailed test, right? This is greater than, so it's a right-tailed test, or a left-tailed test, right? This one is less than, so it's a left-tailed test. So writing our hypotheses in any of these ways works for both paired samples and independent samples. You're going to see for paired and independent samples, you're talking about the same sorts of claims. So we're writing our things in the same way. But for paired samples, right, like paired only over here, we actually have a slightly different way we can write it, because for paired samples, we're getting this difference, right? So let's say the difference is x1 minus x2. Then instead of writing mean 1 minus mean 2 is greater than 0, like this, we can write the mean difference is greater than 0. So this is essentially the same thing as this over here. Right, so for paired samples, we're actually subtracting Bob's rating of recipe A minus Bob's rating of recipe B, and we're getting this difference D. And then if we look at the average difference, we can write the claim in this way. Right, of course, if you did the subtraction the other way around, then that would be the equivalent of this one, right? Then you would get the mean difference is less than 0. So you still have the choice of which way to go with this. right? You can still choose between left tail or right tail based on which way you're doing the subtraction. And so this version on the right, this is what you're usually going to see on your quizzes, I believe. Most of the quiz questions should look like this for paired samples. And on the quizzes, they're usually going to be telling you which way to do the subtraction. In the real world, of course, you can just choose which way to do the subtraction, which group is subtracted from which other group, right? Are we doing x1 minus x2, or are we doing x2 minus x1? In the quiz, they will generally be telling you which way to do it, right? So if they tell you that you're doing d equals x1 minus x2, then you know you need to do this green version here. And if they're telling you that d equals x2 minus x1, then you know you're doing this brown version here. Right? But all of these essentially write the same claim, which is that the mean, group 1 has a larger mean than group 2. So all of these, whichever one we pick, these are all alternative hypotheses. Why are they alternative hypotheses? Well, because the null hypothesis has the equal sign, right? What does the null hypothesis look like? It looks like mean 1 is less than or equal to mean 2. Or mean 1 minus mean 2 is less than or equal to 0. Or mean 2 minus mean 1 is greater than or equal to 0. Or the mean difference is less than or equal to 0. Or the mean difference is greater than or equal to 0, right? Each one of these ways of writing the hypothesis for the alternative hypothesis has a corresponding way of writing the null hypothesis. Right? The null hypothesis is always just the opposite of the alternative. Right? And which one is the null is the one with the equal sign. Right? So you can see this, all these ones on the bottom have either less than or equal or greater than or equal. That's why they're the null hypothesis. All right, let's do another claim. Group 1 has the same mean as group 2. Okay, so group 1 is the same mean as group 2. Well, that's going to be mean 1 equals mean 2. Which is going to be, if we write it in this way with the subtraction, we can write mean 1 minus mean 2 equals 0, or mean 2 minus mean 1 equals 0. Right? It doesn't really matter which way to do subtraction here. You can see either case, we've got two tails, right? We're doing a two-tail test here because we still have equals versus not equals. Right? So when we have mean 1 equals mean 2, this is going to be a two-tail test. And if we're doing it this this paired samples way, then it doesn't actually matter which way we write the subtraction, because it's going to either way, it's going to be mean difference is equal to 0. Right? It's the same thing no matter which way we do the subtraction. 1 minus 2 or 2 minus 1, it's equal to 0 either way. Right? So that's the same claim that group 1 has the same mean as group 2. And then the opposite of that would just be not equals. Right? So if we're doing paired samples, we probably write it this way. And then again, we have to identify which one is the null, which one's the alternative. Well, if we have equals versus not equals, the null is the one with the equal sign. So the first row here, the claim in this case is the null. And the opposite is the alternative. Right? Whichever one has the equal sign is the null. So these are the most common types of claims you're going to see. Seeing a 0 is the most common thing. Usually we're just testing, is this group larger than that group? Or we're testing, are these two groups equal? Those are the most common types of claims. But occasionally you'll get a different type of claim, which is a little bit trickier. So Let's write down a different type of claim. Non-smokers live 7 years longer than smokers on average. This is a claim. So how would we write this? Well, we're saying the mean for non-smokers is the mean for smokers plus 7. Right? It's 7 years longer than the mean for smokers. So that's one way of writing the claim. If we want to do a subtraction, it would be the mean for non-smokers minus the mean for smokers is equal to 7. And you have to be careful because if you use subtraction the other way here, mean S minus mean N, you don't get 7. You get -7. Right? Think about moving the 7 over here algebraically. Move the 7 to the other side, it becomes -7. So these are the 3 different ways we might write this. Now this is an independent samples test, right? We can't do paired samples here. We can't test how long someone lives under two different conditions. So we're doing independent samples here. So I don't need to worry about the paired samples, but it would be the same sort of idea where it equals 7 or equals -7 would depend on which way we did the subtraction. Right? If the difference was smokers minus non-smokers, whatever, which, like I said, we can't really do paired samples that way, but if we could, then we would have to have -7 based on this order, right? So which order you're doing subtraction determines which side things are going to be happening on, right? In this case, if it's a positive or a -7. Now this one trips people up because it's got the word longer, right? If I just said non-smokers live longer than smokers, then you would think, oh, well, that's this. Great, that's the mean for non-smokers is greater than the mean for smokers, right? That's what longer would mean. But if it says 7 years longer, that's saying that the difference is 7, right? It's not saying more than 7 years longer. It's not saying less than 7 years longer. It's not saying at least 7 years longer. It's saying that they live 7 years longer, like exactly 7 years longer. That's the claim being made here. Right? We could see there could be a different claim, which is that non-smokers live at least 7 years longer than smokers. That would be a little bit different, right? See, now we would be saying that the mean life expectancy for non-smokers is at least the mean for smokers plus 7. So we would get the mean for non-smokers minus the mean for smokers is at least 7. Right? And you could do, instead of at least, you could do greater than or less than or whatever, right? Whatever version you wanted. Right? And then here would be the mean. Careful on this one. This one's tricky as well. If you do the subtraction the other way, you get less than or equal to -7. Right? Gotta do a little bit of algebra to go from here to here, right? But if you do the algebra, you'll see it works out that way. Yeah. So with these types of claims, usually we'll write it like this way, because the other way, with the -7, gets confusing. It gets confusing quickly when we have the negatives. Usually we'll just do the longer one minus the shorter one, the larger value minus the smaller value, and then we only have to deal with the positives. We don't have to deal with the negatives. It just makes it a little bit less confusing to do it this way. So usually we'll do it that way, right? Whereas like over here, it didn't really matter, right? Whether it's less than equal to 0, greater than equal to 0, it doesn't really matter. It's still 0 in either case, right? Here, having to swap from a 7 to a -7 because of the way you're doing subtraction, it's confusing. So, like I said, usually we don't worry about that. Okay, so these types of claims are trickier to deal with. but they're not very common. Most of the time we're dealing with claims that are just like greater than 0 or equal to 0 or whatever. Okay, so you might get some quiz or test questions that are about this sort of thing, right? It might be, here's the situation, what are the hypotheses, right? Even if we're not doing the whole, test the whole thing, start to finish, step 1 to step 4, you might get some questions that are sort of like multiple choice questions or fill in the blank questions that are just about testing, just about writing hypotheses. Okay, so that's that. And now, like I said, the last thing I wanted to do today, and then we can call it a day a little bit early, is to just write, just do start to finish an example here. So you are doing a taste test of 2 recipes. You get 8 people in your sample to rate both recipes. Right, so that we're getting the same 8 people to rate both means we're doing paired samples. Now, this is a small sample, right? That's less than 30. So we need an assumption here. You assume that the mean, so you assume that the differences are normally distributed. You have to assume that in order to do what we're doing, because we have a too small a sample otherwise. Right? Without that assumption, we can't do it. If you don't want to have to make assumptions like that, then you just need to sample more people, right? We know this. If you sample 30 or more, then it's all good. You get the following data. So I'm going to make a little table here. So we're going to have eight people. I'm going to have their ratings. Okay, so we have 8 people here, right? The index is in the first column here, these 8 people. And then each person gave us a rating for recipe A and a rating for recipe B. I'm not sure if you can see this while I'm typing it, but just I'm gonna make it visible in just a sec if you can't see it. Sometimes with the whiteboard, it doesn't show up right away. And the question is gonna be, what can you conclude at a significance level of 0.10? Okay, so we have the raw data here. So we can just start at step 1. The way this actually works is we could start doing differences and stuff first, before step 1. There's a little bit of math we have to do with these numbers, right? We have to do some subtractions and stuff, and we'll see a little bit more later. So we can start by doing that math, or we can start at step 1. I'm just going to start at step 1, but I know different people like to do it differently. So for me, step 1, we have to write down the claim, right? So we don't have any particular idea that A is better than B or B is better than A, right? What are we trying to, we're just trying to see what can we conclude from this taste test, right? So we're trying to see, like, is there a difference at all? Right? It's not asking is A better than B, because that would be greater than. It's not asking is B better than A. right? It's just asking, is there any difference at all, right? Can we conclude anything here? So like that, right? Mean A is different from mean B. That's what we're trying to figure out if that's true, right? Is there any difference at all? So then if we want to write that another way, right, we might write like mean A minus mean B equals 0, or because this is a paired samples test, we're going to write it mean D equals 0, where D is equal to A minus B. So we're deciding up here in step 1 which way to do the subtraction, right? Again, on ideas, that's probably going to be given to you. They're going to tell you which way to do it. But if they don't, then you get to decide, I guess. Right? So this is how we're writing. Oops, I should not equals. This is how we're writing the claim. The mean difference is not equal to 0, right? In other words, there is a difference. And then the opposite is the mean difference is equal to 0. So this is the alternative, and this is the null. Right? So this is what our step 1 might actually look like. These are our hypotheses. Then in step 2, we're going to do the same thing we did in last week, right? We're going to look on the t-table. So we need to know what column. So what column are we in? Well, this is equals versus not equals. So this is two-tail. And we're given the alpha equals 0.10. And then for rho, the degrees of freedom should be n minus 1. So that's 8 minus 1, which is 7. So we need to go to our t-table and look at the two-tail alpha equals 0.1 and rho 7. So give me a sec here to pull up that t-table. Where's my t-table on? All right, so here's the t-table. We're looking at two tails alpha is 0.1, so we're looking at this column here, and we're looking on row 7. So there we are, 1.895. 1.895 is our critical value. All right, so this is T alpha over 2 is 1.895, and it should be plus or minus because we're doing two-tail here. All right, so what are we going to say? We're going to reject the null hypothesis when T is greater than 1.895 or T is less than negative 1.895. Okay, so that's step 1 and step 2. Right, step 1, we have to think about this, how do we write the claims? Step 1, like I said, is the most different from last week. Step 2 is not different from last week. Step 2 is exactly the same as last week. Step 3, we have a formula now, right? The formula says that the test statistic is equal to, now if you remember last week, it looked like x bar minus the mean over standard deviation over square root n. Well, this time it's going to look like d bar minus the mean difference over the standard deviation of the differences over the square root of n. It's really the same formula. It's still sample mean minus population mean over standard deviation over square root n, right? It's really the same formula. Now, we have to think, what do we actually have already? So this mean difference, we always find that from the hypotheses, from back up in step 1. That's the 0 here. right? So this is going to be minus 0. And then in the denominator, we know what this root n is, right? That's the 8 people. Right? So we're going to get over the square root of 8. But we have to pause here and think, well, we weren't actually given the sample mean or the sample standard deviation. We weren't given those things in this question. And now sometimes the question will give you those things, right? If the question gives you those things, then you can just go ahead and punch them in, right? And plug them into your formula and do that, get your answer. But if the question doesn't give you those, what are we going to do? We're going to calculate them ourselves. Right? So that's what we're going to do over here now, is we're going to calculate these ourselves. So we start by getting the differences. Now, in part 1, we said we were going to do a minus b as opposed to b minus a. Right? So we're doing a minus b. So 7 minus 7 is 0. 9 minus 6 is 3. 7 minus 5 is 2. 6 minus 2 is 4. 10 minus 9 is 1. 8 minus 4 is 4. 5 minus 6 is negative 1. And 8 minus 5 is 3. These are our differences. Right? So that's just subtraction. So now we want to add those up. Right? So 0, 3, 5, 9, 10, 14, 13, 16. They add up to 16. That's the total. Right? So what's d bar? The sample mean, that's going to be 16 over 8, which is 2. The sample mean is 2. Right? So far, so good. That's not a big deal. Right? This comes from the total. The sample standard deviation is a little bit trickier, but we did this in the first term, right? In the first half of the course, we did these sample standard deviations, so we know how to do it. So you just have to do like we did before, right? Subtract the mean, and then square it, get the deviations, square them. Right? So 0 minus 2 is negative 2. 3 minus 2 is 1. 2 minus 2 is 0. 4 minus 2 is 2. 1 minus 2 is negative 1. 4 minus 2 is 2. Negative 1 minus 2 is negative 3. And 3 minus 2 is 1. And if we add those up, we should get 0. You can double check. Do we get 0 here? Negative 2 and 2, 1 and negative 1. Yep, we get 0. So that's good. And then we square these. Negative 2 squared is 4. 1 squared is 1. 0 squared is 0. 2 squared is 4. Negative 1 squared is 1. 2 squared is 4. Negative 3 squared is 9. And 1 squared is 1. So we're squaring each of these. And then we add these up. 5, 10, 15, 24. So then our standard deviation, our sample standard deviation, we have to do 24 divided by, what do we divide by? N minus 1, right? It's a sample standard deviation. So it's n minus 1. We're dividing by 7. And then we're going to take the square root. Okay, so 24 divided by 7, and then take the square root. Where's my square root button? There it is. 1.852. That's my standard deviation. Right, so this 1.852 comes from this calculation, which comes from all that stuff. So when we're doing this type of question, right, if they want to give us the full version where we have to calculate everything from the raw data, then it's like doing one of the questions from last week, plus doing a standard deviation question from the first half of the course, all in one, right? This is like the biggest version of this question. They don't have to give us just the raw data, right? Sometimes they can give us the sample mean and the sample standard deviation of the differences without making us calculate them. But if they make us calculate them, if they just give you the raw data, you know how to do it, right? We did this in the first half of the term. You can calculate that mean and that standard deviation yourself. And then we plug these in and we see, what do we get? Let me see here. Oh, I gotta bring up my calculator again. We're getting 3.05. And so that's our test statistic. That's step 3, right? Step 3, just using the formula. Step 3 itself is pretty easy, but in this case, it just required us to do some work to get that mean and that sample standard deviation. Right? And this is what I was saying. You could do that before you even do step 1, right? Like when they give you the data, if you want to do this stuff on the left first before you even start writing step 1 and step 2, you can do that, right? You can kind of do things in whatever order you want to some extent, right? Step 2 has to come after step 1 because you have to know which way you're doing the subtraction. You have to know what the hypotheses are, but whether you want to do all this math of calculating the sample standard deviation and sample mean before you start is up to you. Anyway, step 4 now is just the conclusion, which is easy enough, right? So 3.05 is bigger than 1.895, right? So we reject the null hypothesis. What did the null hypothesis say? The null hypothesis, remember, was this one over here. The null hypothesis said the mean difference equals 0. In other words, there's no difference, right? The null hypothesis says there's no difference between the two recipes. And we reject that. We reject that. We have enough evidence that we are convinced that there is a difference between the recipes. We are convinced, right? So we have enough evidence to say there is a difference in the mean ratings of the two recipes. Right? We are convinced there's enough evidence. And in particular, if we actually look at what happened, right, recipe A was better than recipe B. Right? Everyone rated recipe A better than recipe B except for 2 people, one of whom said it was a tie, and the other one who rated recipe B better just by a slight bit. Right? Overall, the consensus was recipe A is the better recipe. And there's enough evidence here to say that that's actually convincing. Right? With a small sample size like this, only 8 people, it's hard to get convincing evidence. Right? So the fact that it was, almost unanimous, the fact that it was, that we got enough evidence means that there was quite a big difference between those recipes. In this small sample. Okay, so that's the full thing. That's the whole big question. On your quiz, you're going to get maybe some questions asking you to do parts of this at a time, but you might also get a question asking you to do the whole thing, start to finish. Right, so this is what the whole thing looks like, start to finish. Any questions? Okay, so we'll just wrap it up here for today. Next week, we're going to talk about how we actually do the independent samples testing. And so we're going to do the independent samples testing. And if we have more time, which we probably will, we're going to do the hypothesis testing with proportions. Now, one thing that's important to note is that this paired samples test is also called dependent, right? Dependent versus independent is what some people say. I usually say paired versus independent, but dependent is another way of writing it. And importantly, this is not quiz 9, this is quiz 10. All right, so I did module 10 before module 9, just because I think it's better to do module 9 in person. So when you're doing the quizzes or whatever, the topic we covered today was quiz 10. We're covering quiz 9 next week. All right, so I've done it slightly out of order from how it is on ideas. And because of that, I'll probably just extend quiz 9. Yeah, I'll just make quiz 9 do at the same time as quiz 10 is. All right, so you can do them together or whatever. Or you can do quiz 10 now and then do quiz 9 later. Okay. All right, so that's it for today. And if no one has any questions, then we'll call it a day here. Oh, I have someone asking a question in the direct messages. There's 2 questions. Okay, so one of them is about the material and one of them is about the quiz and assignment. It says quiz 9 and assignment 4 are due on the same day. Let me just check out assignment 4 and make sure I remember exactly what's on it. Assignment 4 has assignment 4 does have some stuff with independent samples, so I should extend that as well. Thanks for pointing that out. Okay, I'm extending assignment 4, same as quiz 9. The other question that I got here in the direct messages was, if you're given the test statistic, can you calculate alpha? And no, alpha is not something that you calculate. Alpha is something that is given by the question, right? Now, what you might be asking about is on your assignment, there's a question that says, for this test statistic, you would reject the null hypothesis at which values of alpha? And so to figure that out, what you need to do is for each value of alpha, you're going to get a different critical value. And so if you calculate the critical values, or not calculate, but look up on the table, the critical values for each alpha, then you can compare the test statistic to each of those and see for which of those would you reject and for which of those would you not reject. But we don't calculate alpha, right? Alpha is something that is given or decided on, not calculated. You can calculate a p-value from the test statistic, and then compare that to alpha, but that's different. Right, so if the question is about the assignment, then like I said, for each alpha that's on the multiple choice answers, you're going to calculate or look up on the table a critical value, and then you can compare your test statistic that's given in the question to each of those critical values and see which ones get rejected and which ones don't. All right, any other questions before we go? Okay, have a good week, everyone. We should be back in person next week. I'll see you then.